as a first example, let's find the area of the region which is inside the cardioid r equals 1 plus cos theta. So that's this. And outside the circle r equals 1. So our region is just this part. So first, let's find the bounds. So we can sort of see from our sketch, but to see how this, to do this just from the equations, so we'll set these two values of r equal to each other. So 1 equals 1 plus cos theta implies cos theta is 0, implies theta is plus or minus pi over 2, as we can see in this picture. So if we integrate so I guess we can, all we need from here is the theta. Okay, so if we integrate r, and we'll integrate in the order dr d theta, so that looks like this, then our bounds for theta will be negative pi over 2 and pi over 2. And our bounds for r are, so r is always going from 1 to 1 plus cos theta. Okay, so that becomes integral negative pi over 2 to pi over 2. And so we integrated r squared, or sorry, we integrated r, so that'll give r squared over 2. So we have 1 plus cos theta squared minus 1 squared all over 2 d theta. So that becomes integral negative pi over 2 to pi over 2 of cos theta plus cos squared theta over 2 d theta. And so this is sine theta, and then using number 66 from the table of integrals at the back of the book, this will be plus theta over 4 plus sine 2 theta over 8 at pi over 2 and negative pi over 2. So this is the indefinite integral of this part. And so then we can evaluate that. So that is 1 plus pi over 8 plus 0 minus minus 1 minus pi over 8 plus 0 is 2 plus pi over 4 is the area of this region. Next, we'll find the area of the region enclosed by a by the spiral r equals 4 theta over 3. So here's that spiral, and the negative x-axis. So here's our region. So first let's do this. So if we integrate with respect to r first, which typically is a good idea, we'll get a equals integral something r dr d theta. So this is what it looks like integrating with respect to r first. Theta goes from 0 to pi, and then r goes from 0 to 4 theta over 3. So that so that'll become integral 0 to pi of r squared over 2 at 4 pi over 3 and at 0. And so that's equal to integral 0 to pi 8 theta squared over, not over 2, over 9 d theta, which is 8 pi cubed over 27, or we could also write this as 2 pi over 3 cubed. Now, usually it's not a good idea to integrate, or oftentimes if we integrate in the other direction, things go very bad. But in this case, so for instance, the previous example, if you tried to do with respect to theta first, things would go bad, as you can try. So if we integrate with respect to theta first, so now this will be something d theta dr, and this is what that would look like. So r is going from 0 to 4 pi over 3. That's the coordinate of on the far left, where the farthest left we can go. And then theta, so theta will always be going all the way to the x-axis. So the upper limit is pi, and the lower limit will be 3r over 4, r d theta dr. Okay, so that becomes integral 0 4 pi over 3 of pi r minus 3r squared over 4, and then everything, this is dr. So integral 0 4 pi over 3 pi r minus 3r squared over 4 dr is, so that'll be pi times 4 pi over 3 squared over 2 minus 4 pi over 3 cubed over 4. So let's see, this will give us, let's try to factor out as much as we can. So if we get rid of the pi's, we'll have a pi cubed. Then here we've got over 3 cubed. And so I need to add a 3 here to factor out this 3. Then we'll have 4 squared over 2 is 16, so this is 8. And then here 4 cubed over 4 is just 4 squared, so this will be 16. So then this is 8 times 3 minus 16. And so that's 8. So we get 8 pi cubed over 3 cubed, which again, so I did 8.3 minus 16 is 8. And again, that's 2 pi over 3 cubed. As a final example, we'll find the area of the region which is common to the interiors of two cardioids. So the cardioid r equals 1 plus cos theta and r equals 1 minus cos theta. So our region that we're interested in is this green shaded region. But by symmetry, we can calculate just one of those and then multiply the result by 4. Okay, so our area is going to be 4 times some integral. So we'll do it again in the order dr d theta. So theta, we can see now that we've removed the, now that we focus just on this one quarter, we'll go from 0 to pi over 2. That's going up to the y-axis. And then, so in this sector, we're using r equals 1 minus cos theta. So r will go from 0 to 1 minus cos theta. Okay, so let's evaluate this integral. So this is 4 integral 0 to pi over 2. So integral of r is r squared over 2. So this will be 1 minus 2 cos theta plus cos squared theta all over 2 d theta. Now there's a trick we can use to simplify this integral without having to go through the integral of cos squared theta. So remember that cos 2 theta is equal to 2 cos squared theta minus 1. So we can rewrite our integral as integral 0 pi over 2. We'll try to, so this will be 2 cos squared theta. So I'll bring the 2 in, 2 cos squared theta minus, actually I want this, so I want this minus 1, and so then I have to add plus 1, and then, so we get this. So then this part we can rewrite as, so this becomes integral 0 to pi over 2 of cos 2 theta minus 2 cos theta plus 3 over 2. And then this is all d theta. Now, the reason I did that is that cos 2 theta, well, if we're going theta from 0 to pi over 2, then 2 theta will go from 0 to pi, and that's integrating a function over, like, sort of the negative and positive values of this will cancel out. So this, without even having to do any anti-differentiation, we can cancel out to 0. So that you don't have to do it that way. You could go through the integral of cos squared, but sometimes you can spot this trick. So our area, now that we've brought, this should be 3, not 3 over 2. And I think this also should be a 4. Yeah, sorry about that. Doing too many simplifications at once. Okay, so integral 0 to pi over 2 of 3 minus 4 cos theta d theta is 3 theta, or no, minus 4 sine theta at pi over 2 and at 0. And so that will be 3 pi over 2 minus sine of pi over 2 minus 4. And then, yeah, the other values at 0 don't contribute. So the area of the original region, so all 4 of them, is 3 pi over 2 minus 4.